For a single, fleeting moment, everything you are, every atom in your body, every star in the sky, every galaxy in the cosmos was compressed into a point of infinite density, a place smaller than a single grain of sand. What if I told you the story of everything started not with a bang, but with a whisper? A moment of cosmic silence that shattered into reality itself. We're about to rewind time 8 billion years to uncover the most incredible truths about our universe's birth. If you love exploring the cosmos, hit that subscribe button and let's rewind the clock. Our story begins in an era so extreme that our laws of physics simply cease to exist. Forget seconds or even nanoseconds, we're going back to the very first tick of cosmic time, a period known as the Planck epoch. This slice of existence lasted for just 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second. Within this unimaginable flicker, the four fundamental forces of nature that govern everything, gravity, electromagnetism, and the two nuclear forces, weren't separate entities. They were merged into a single, unified superforce. The temperature was a staggering 10,000 trillion degrees, a temperature so high that the very concepts of space and time become scrambled and uncertain. We can't describe this state. General relativity, our theory of the very large, and quantum mechanics, our theory of the very small, both break down. It is the ultimate physical mystery, the point before which there was no before. From this crucible of pure potential, the first great separation occurred. As the universe took its first breath, it cooled just enough for gravity to split off from the other three unified forces. This kicked off a new phase, the Grand Unification Epoch. But the universe wasn't done yet. A mere fraction of a second later, the strong nuclear force broke away, and in doing so, it unleashed the single most violent and transformative event in cosmic history: inflation. This wasn't an explosion moving through space, it was an explosion of space itself. In an instant shorter than the time it takes light to cross a single proton, the universe expanded exponentially, growing by a factor of at least a trillion. It leaped from being smaller than an atom to roughly the size of a grapefruit. This hyper-expansion is the reason our universe is so incomprehensibly vast today. It also ironed out the fabric of space-time, smoothing out any initial wrinkles and making the universe appear remarkably uniform and flat on the largest scales, a cosmic puzzle that inflation elegantly solves. After this frantic expansion, the universe was now a seething, scorching inferno, but it wasn't filled with atoms or even protons and neutrons. At about 1/1,000,000th of a second old, it was far too hot and dense for those to form. Instead, it was filled with a bizarre state of matter known as the quark-gluon plasma. Imagine a soup where the fundamental building blocks of matter, tiny particles called quarks, roamed freely, bound together by the carriers of the strong force, gluons. This primordial substance, the consistency of which has been described as a perfect liquid with almost zero friction or viscosity, filled all of space. We've even managed to recreate this state of matter for tiny fractions of a second in particle accelerators here on Earth, giving us a direct window into the universe's first moments. What do you think would be the strangest thing to see if you could somehow peer into a real quark-gluon plasma? Drop your most creative ideas in the comments below. As this cosmic soup continued to cool, it faced an existential crisis. The laws of physics demand that energy can create particles, but it must do so in matter-antimatter pairs. For every electron, an anti-electron, or positron, is born. For every quark, an antiquark. When these pairs meet, they annihilate each other, vanishing into a puff of pure energy. In the early universe, this should have been a perfect stalemate. Matter and antimatter should have been created in equal amounts, and then, as the universe cooled, they should have all found a partner and annihilated, leaving behind a vast, empty cosmos filled with nothing but leftover radiation. But that's not what happened. For some reason, a tiny asymmetry crept in. For every billion antimatter particles, the universe cooked up 1,000,000,001 matter particles. After the Great Annihilation was over, that 1 in a billion survivor was all that was left. Everything you see, every star, every planet, every living thing is made from the tiny fraction of matter that won this cosmic lottery. We still don't know exactly why this imbalance occurred, but without it, none of us would be here to ask the question. For the next 380,000 years, the universe was a place of blinding light, but also a place of total opacity. It was a glowing, impenetrable fog. The temperature was still so high that electrons couldn't settle down. They whizzed around as free agents, unbound to the newly formed protons and helium nuclei. Photons, the particles of light, couldn't travel more than a few steps without slamming into one of these free electrons, getting scattered in a random direction. Light was trapped in a cosmic pinball machine. But as the universe kept expanding, it kept cooling. When the 380,000-year mark finally arrived, the temperature dropped to about 3,000 degrees Kelvin. This was the magic number. It was finally cool enough for the frantic electrons to be captured by the atomic nuclei, forming the first stable, electrically neutral atoms of hydrogen and helium. This pivotal moment is called recombination. And in an instant, the universe's character changed forever. With the electrons now locked into atoms, the photons were suddenly free. The cosmic fog lifted. For the very first time, the universe became transparent. The light that was unleashed at that exact moment is still traveling across the cosmos today, and we can still see it. After its epic journey of 13.8 billion years, that ancient light has stretched and cooled, and it now bathes the entire sky not as visible light, but as a faint, cold glow of microwaves. This is the cosmic microwave background radiation, or CMB. It is, without exaggeration, the single most important source of information we have about the early universe. It isn't just a uniform glow, it's a photograph. It's the universe's baby picture. Imprinted upon it are minuscule temperature fluctuations, tiny variations that differ by only 1 part in 100,000. These aren't imperfections, they are the seeds of everything. The slightly hotter, denser patches were the regions where gravity had just a little more pull. Over hundreds of millions of years, these tiny seeds would slowly draw in more and more matter, collapsing under their own weight to form the very first stars, the first galaxies, and eventually the vast cosmic web that structures our universe today. By studying this fossil light, we have confirmed the age of the universe, mapped its geometry, and even precisely measured its ingredients. A humble 5% normal matter, 27% mysterious dark matter, and a dominant 68% reality-bending dark energy. It is the echo of creation itself, and that's just the first 380,000 years. The universe was transparent, but it was also dark and silent, a vast expanse of neutral gas waiting for the first sparks of light to ignite. The cosmic dark ages were about to begin. If your mind was expanded today, be sure to hit that like button and subscribe so you don't miss our next journey into the darkness before the dawn of the first stars. Imagine for a moment that the sun simply vanished. Poof, gone. For a full 8 minutes, you wouldn't know. The Earth would continue its serene journey around a star that no longer exists, basking in ghost light, held in place by a ghost's embrace. Why? Because the message that the sun is gone, the news carried by gravity itself, is still on its way. That message, that fundamental whisper that organizes the entire cosmos, is what we call gravity. It feels so simple, so intuitive. You drop an apple, it falls. But this everyday force is a mask for one of the deepest, most bizarre, and most beautiful concepts in all of physics. It's a force that isn't a force, a pull that's actually a push from the fabric of reality itself. Let's start with one of the biggest paradoxes. Of the four fundamental forces of nature, gravity is, by a staggering margin, the weakest. It's comically feeble. A tiny refrigerator magnet can lift a paperclip, its electromagnetic force effortlessly overpowering the entire gravitational pull of the 6 septillion kilogram planet beneath it. Yet, look up at the night sky. Every star, every galaxy, every colossal cluster of galaxies is held together by this same weak force. So how does the weakest player on the team run the entire game? It's because gravity has two killer advantages: infinite range and an inability to be canceled out. While other forces have positive and negative charges that neutralize each other, gravity is always attractive. Every single particle with mass adds to the pull. Over cosmic distances and with immense collections of mass, this ever-present, ever-adding up influence becomes the undisputed architect of the universe. But here's where it gets truly strange. Albert Einstein completely redefined our understanding of this cosmic architect. He revealed that gravity isn't a force pulling you down at all. Instead, mass and energy literally warp the fabric of space-time around them. Picture a bowling ball placed on a stretched-out rubber sheet. The sheet curves and dips. Now roll a small marble nearby. The marble doesn't get pulled toward the bowling ball. It simply follows the straightest possible path through the curved space created by the bowling ball's mass. That's you. That's the Earth. We aren't being pulled by the sun. We are following a straight line through the curved space-time created by the sun's immense mass. That path just happens to be a nearly circular orbit. So the feeling of being pulled down is actually the sensation of the universe's geometry pushing up on you. This leads to a mind-bending consequence for your everyday life. Right now, as you sit there, you are technically in a state of perpetual freefall toward the center of the Earth. Your body's natural trajectory, your straight line through curved space-time, is to fall. The only thing stopping you is the electromagnetic force of the chair or floor pushing back up on your body, constantly interrupting your fall. Astronauts on the International Space Station aren't floating because there's no gravity. In fact, the gravity up there is about 90% as strong as it is on the surface. They are floating because they and their station are in a constant, unimpeded state of freefall, endlessly falling around the Earth. They are simply following their natural path through space-time. You would be too, if it weren't for the ground getting in the way. Now, we think of that gravitational push as being uniform, but our planet is not a perfectly smooth marble. The Earth bulges at the equator due to its rotation and is slightly flattened at the poles. It's also lumpy, with varying densities in its crust and mantle. Because gravity is so sensitive to mass and distance, its strength actually changes depending on where you are. You would weigh about 0.5% less at the equator than you would at the North Pole, simply because you're slightly farther from the planet's center. There are even strange gravitational dead spots, like the Hudson Bay area in Canada, where gravity is measurably weaker than surrounding regions, a lingering effect from the crushing weight of ancient glaciers that have since melted. If you could measure your weight anywhere on Earth with perfect precision, where would you go to weigh the least? Let me know your travel plans in the comments. This ability of mass to warp space-time doesn't just keep our feet on the ground. It's so powerful it can bend the path of light itself. Einstein predicted that light from a distant star passing by a massive object like our Sun would be visibly bent. This was famously confirmed during a solar eclipse in 1919. On a cosmic scale, this effect is spectacular. Entire galaxies and galaxy clusters, with their immense mass, act as natural magnifying glasses in space. This phenomenon, called gravitational lensing, allows astronomers to see objects that are directly behind the massive cluster, objects that would otherwise be completely hidden from our view. Sometimes the light is distorted into beautiful arcs and rings, known as Einstein rings, giving us a warped, almost surreal peek into the deepest, most ancient parts of the universe. For all we know about it, gravity holds one of the biggest secrets in modern physics. We have a fantastically successful theory for the very small, quantum mechanics, and an equally successful theory for the very large, general relativity. The problem is, they don't work together at all. Physicists are desperately searching for a theory of quantum gravity to unite them. In the quantum world, other forces are carried by particles. Electromagnetism has the photon. The strong force has the gluon. Gravity, theoretically, should have one too, a hypothetical particle called the graviton. But because gravity is so incredibly weak, gravitons would be almost impossible to detect. They would interact so rarely with matter that a detector the size of Jupiter, placed right next to a neutron star, would only be expected to spot one graviton every decade. It remains one of the greatest missing pieces in our puzzle of the cosmos. And that brings us back to that vanishing sun. The idea that gravity's influence isn't instantaneous was a direct consequence of Einstein's theories. He showed that nothing, not even information, can travel faster than the speed of light. This includes the information that a massive object is present. In 2015, this was proven directly. Scientists at LIGO detected gravitational waves for the first time, ripples in the fabric of space-time itself, caused by the collision of two black holes over 1 billion years ago. By measuring their arrival time, we confirmed that gravity propagates at exactly the speed of light. So that embrace holding our solar system together isn't a rigid, instantaneous cage. It's a dynamic, rippling field, a message traveling across the void at 300,000 kilometers per second, constantly updating the universe on where everything is and where it's going next. Imagine trying to catch your own shadow. No matter how fast you run, it's always right there with you, untouchable. Now, what if I told you that in the universe, there's something you couldn't even get close to catching, a fundamental speed limit woven into the very fabric of reality itself? We think of light as simple illumination, the thing that lets us see the world. But the truth is, light is one of the strangest, most paradoxical, and most powerful forces in the entire cosmos. Its secrets are the secrets of reality itself. We have to start with its most famous property, its speed. The speed of light in a vacuum is the universe's absolute, unbreakable speed limit, clocking in at an almost incomprehensible 299,792,458 meters per second. This isn't just a record to be broken, it's a fundamental constant of nature, a rule that everything in the cosmos must obey. Nothing, no information, no object, no spaceship can travel faster through space. It's so fundamental that we've actually redefined our units of measurement around it. The meter is now officially defined as the distance light travels in a vacuum in 100, 299, 792, 458 of a second. We didn't just measure the speed of light, we made it the ultimate ruler of the universe. So why is this speed limit so absolute? The answer lies in Einstein's most iconic equation, E equals mc squared. While we often associate it with atomic energy, its deeper meaning is a profound statement about the relationship between mass and energy. It tells us that mass is just a super concentrated form of energy. As an object with mass accelerates and approaches the speed of light, its kinetic energy increases. But according to this equation, that added energy also increases its effective mass, making it harder and harder to accelerate further. To push an object with even a tiny bit of mass all the way to the speed of light, you would need an infinite amount of energy, because its mass would become infinite. The universe literally doesn't have enough energy to make it happen. But this is where light plays by its own set of rules. It gets stranger, because light itself seems to be having an identity crisis. Physicists have confirmed that light exhibits a bizarre property called wave-particle duality. This means that sometimes it behaves exactly like a continuous wave, spreading out, interfering with itself, and creating patterns just like ripples in a pond. But at other times, it behaves like a stream of individual, discrete particles called photons. What's truly mind-bending is that the very act of observing it can force it to choose which property to display. In the famous double-slit experiment, if you don't watch which slit a photon goes through, it acts like a wave and goes through both at once, creating an interference pattern. But if you set up a detector to see which slit it passes through, it instantly collapses into a particle, passing through only one, and the wave pattern vanishes. It's as if reality itself is uncertain until we look at it. The reason light can pull off these incredible feats comes down to its constituent particle, the photon. A photon is a truly bizarre entity because it has zero rest mass. It is a pure packet of electromagnetic energy, always in motion. Because it has no mass, it isn't bound by the rule that requires infinite energy to reach light speed. For a photon, traveling at speed c is not just its top speed, it's its only speed. A photon can never slow down or speed up in a vacuum. From the moment of its creation to the moment of its absorption, it exists in a state of perpetual motion at the cosmic speed limit. And here's the wildest part. From a photon's own perspective, because of the effects of relativity at that speed, no time passes at all. Its entire journey across billions of light years happens in an instant. This constant, finite speed has a staggering implication for how we view the universe. Every time you look up at the sky, you are quite literally looking into the past. The light from the sun doesn't reach us instantaneously. It takes about 8 minutes and 20 seconds to travel the 93 million miles to Earth. So if the sun were to suddenly vanish, we wouldn't know about it for over 8 minutes. The light from our next nearest star, Proxima Centauri, is over 4 years old. The Andromeda Galaxy, the most distant object visible to the naked eye, appears to us as it was 2.5 million years ago. We are seeing the light of stars that may have already died. Every telescope is a time machine, allowing us to witness cosmic history firsthand. If you could somehow view Earth from 65 million light-years away, what moment in its history would you most want to see? Let me know your thoughts in the comments below. Now, if light always travels in a straight line, how can we see images of galaxies that are hidden behind other galaxies? Because another of Einstein's revelations tells us that it doesn't always travel in a straight line. According to his theory of general relativity, massive objects don't just pull on things with gravity, they fundamentally warp and curve the very fabric of space-time around them. And since light must travel through this space-time, its path gets bent as it passes by these massive objects. This phenomenon is called gravitational lensing. A huge galaxy or cluster of galaxies can act like a cosmic magnifying glass, bending the light from an object behind it and creating distorted, magnified, or even multiple images of the distant object for us to see. It's one of the most powerful tools astronomers use to map out invisible dark matter and peer at the universe's most ancient galaxies. So, the speed of light in a vacuum is constant and unbreakable. But what happens when it's not in a vacuum? Well, then things get really weird because light can be slowed down drastically. When light passes through a medium like water or glass, it slows down because it is constantly being absorbed and re-emitted by the atoms in the material. But scientists have taken this to an incredible extreme. By firing a laser through a specially prepared cloud of atoms cooled to just a fraction of a degree above absolute zero, a state of matter called a Bose-Einstein condensate, researchers have managed to slow light down to just 17 meters per second, roughly the speed of a bicycle. And in 2001, they went even further. They managed to bring a pulse of light to a complete and utter stop, held it within the atom cloud, and then released it, sending it on its way again. They effectively stored light, proving that even the fastest thing in the universe can be put on pause. From the cosmic vastness of galaxies and black holes, we now plunge into a reality so small, so strange, it makes science fiction look mundane. We're entering a world where the rules of our everyday lives are not just bent, but completely shattered. This is the quantum realm, and its truths are more bizarre than you can possibly imagine. Here, at the fundamental level of existence, we find that a single particle, like an electron, doesn't have a fixed location. Instead, it exists in a cloud of probabilities, a ghostly haze of potential. It is simultaneously here, there, and everywhere in between, a state known as superposition. It's only when we try to measure it, to pin it down and look at it, that the universe forces it to choose a single spot. It's like a spinning coin that is both heads and tails at once. The moment it lands on your hand is the moment its fate is decided. Before that, it's all just potential. This isn't a guess or a theory, it's the foundational principle that makes everything from lasers to computers possible. But this ghostly uncertainty leads to something even stranger. Imagine you have two of these spinning coins or particles, and they are linked in a special way. Now you can separate them. Send one to the other side of the room or the other side of the galaxy. It doesn't matter. The instant you look at your particle and it chooses to be heads, you know with absolute certainty that its distant twin has instantly chosen to be tails. This instantaneous connection is called quantum entanglement. Information appears to travel between them faster than the speed of light, a phenomenon that baffled even Einstein, who famously called it spooky action at a distance. This isn't communication in the classical sense. No message is sent. It's as if the two particles are two parts of a single system, forever connected by an invisible thread, their fates intertwined no matter how vast the distance separating them. Modern experiments have confirmed this spooky link is very real, challenging our deepest intuitions about space and separation. This incredible interconnectedness reveals another, perhaps even more profound truth about the quantum world. The universe doesn't just put on a show for us. Our very act of watching changes the performance. This is known as the observer effect. In the famous double-slit experiment, when we fire particles like electrons at a screen with two openings, they behave like waves, creating an interference pattern on the other side, as if each particle went through both slits at once. But here's the twist. If you place a detector at the slits to see which one the electron actually goes through, the wave behavior vanishes. The pattern disappears. The electron suddenly acts like a simple solid particle going through one slit or the other, just as you'd expect a tiny baseball to. The mere act of observation, of gaining information about its path, forces the particle to abandon its ghostly, wave-like state of possibilities and collapse into a single, concrete reality. It's as if the universe holds its breath until it's being watched. This ability to be in many places at once allows for another impossible feat: quantum tunneling. According to classical physics, if you don't have enough energy to get over a barrier, you're stuck. If you throw a ball at a wall, it will bounce back. It will never, ever just appear on the other side. But in the quantum realm, particles play by different rules. Because their location is a wave of probability, there's a tiny but non-zero chance that the particle can be found on the far side of a barrier it shouldn't be able to cross. It doesn't break the barrier down, it simply appears on the other side, as if it tunneled through an invisible wormhole. This isn't just a theoretical curiosity, it's happening constantly. Quantum tunneling is the reason our sun can fuse hydrogen into helium, powering all life on Earth. It's also the principle behind modern electronics, allowing electrons to jump across insulating gaps in flash memory and microchips. The impossible is not only possible, it's essential. As we go even smaller, the weirdness intensifies. The vacuum of space, which we imagine as perfectly empty and still, is actually a seething, chaotic mess at the quantum level. This is the concept of quantum foam. At incredibly tiny scales, far smaller than an atom, space-time itself is thought to churn violently. Tiny, virtual particles and their antimatter counterparts are constantly popping into existence from nothing, existing for a fleeting moment, and then annihilating each other in a flash of energy. This isn't an empty stage, it's a frantic, bubbling cauldron of energy and matter, a cosmic static that underpins all of reality. This foam isn't just theoretical. Its effects can be measured, subtly pushing on fundamental particles. It suggests that the smooth, predictable fabric of space-time we perceive is just an illusion, a calm surface on a deep and turbulent ocean. If you could witness this quantum foam for just a second, what do you think you'd see? Drop your most creative description in the comments below. Yet, amid all this chaos and uncertainty, there is a powerful rule that brings order and structure to the universe. It's called the Pauli exclusion principle, and it's the reason matter as we know it can exist. The principle states that no two identical fundamental particles, like electrons, can ever occupy the exact same quantum state at the same time in the same place. It's like a cosmic game of musical chairs where every electron must have its own unique seat. This is why atoms have distinct electron shells, creating the rich diversity of the chemical elements. If this principle didn't exist, all the electrons in an atom would collapse into the lowest energy level, and chemistry, biology, and life would be impossible. More fundamentally, it's the reason you don't fall through the floor. The electrons in your shoes are repelling the electrons in the floor, fiercely defending their own quantum territory. The solidity of the world around us is a direct consequence of this fundamental rule of exclusion. Ultimately, this entire bizarre ballet boils down to one central, mind-bending idea: wave-particle duality. Every single fundamental entity in the universe, whether it's a particle of light, like a photon, or a particle of matter, like an electron, has two faces. Sometimes it behaves like a discrete, localized particle, a tiny little billiard ball. At other times, it behaves like a spread-out, ethereal wave. It's not one or the other, it is, somehow, both at the same time. Which face it shows us depends entirely on how we choose to measure it. This duality is the central mystery of quantum mechanics. It tells us that our common-sense categories of thing and wave are simply too limited to describe the true nature of reality. The universe isn't made of one or the other. It's woven from a substance that is profoundly, beautifully, and bizarrely both. Take your hand and place it on the table in front of you. It feels solid, right? Unyielding. But the truth is, the atoms making up your hand and that table are over 99.999999% empty space. If you squeezed all the empty space out of every human on Earth, the entire population would fit inside a single sugar cube. That staggering emptiness is where our journey begins today, as we rip away the fabric of the familiar and stare into the core of matter itself. If you're ready to have your mind reassembled, make sure you're subscribed and hit that like button to join our quest for knowledge. So let's start with that emptiness. We're taught that atoms have a nucleus with electrons orbiting it. But that mental image is misleading. The scale is impossible to draw. In fact, if the nucleus of a hydrogen atom were the size of a basketball in the center of a stadium, its lone electron would be a tiny grain of sand buzzing around the outermost seats. Everything in between? Nothing. Pure, empty space governed by electromagnetic fields. The feeling of solid is just the electromagnetic repulsion between the electron clouds of your hand and the table. You've never truly touched anything in your entire life. For decades, we thought the story of matter ended with protons, neutrons, and electrons. They were the indivisible building blocks. But physics loves a plot twist. It turns out that protons and neutrons aren't fundamental at all. They're more like tiny, frantic bags holding even smaller particles. Each proton and each neutron is actually composed of 3 smaller particles called quarks, which are genuinely, as far as we know, fundamental. They can't be broken down any further. This means the vast majority of the stuff that makes you isn't even the main character. It's a composite being, a structure built from even stranger ingredients. And these ingredients are bizarre. There aren't just 1 or 2 types of quarks. Physicists have discovered 6 different kinds, which they whimsically named flavors. The ones that build our world are the up and down quarks. A proton, for instance, is made of 2 up quarks and 1 down quark. A neutron is 1 up and 2 downs. But then things get strange. There are 4 other, much heavier and more unstable flavors: the charm quark, the strange quark, the top quark, and the bottom quark. These exotic particles don't stick around. They existed in abundance in the high-energy chaos of the early universe, and can now only be created for fleeting moments in powerful particle accelerators. And to make it even weirder, quarks have fractional electrical charges. Unlike the neat +1 or -1 charges we're used to, an up quark has a charge of +2/3 and a down quark has -1/3. Nature's math, it turns out, is a fan of fractions. Now, if quarks are the ultimate building blocks, you'd expect we could just pull a proton apart and study one, right? Wrong. Nature has a rule that is, for all intents and purposes, absolute. You are not allowed to see a quark by itself. This principle is called color confinement. The force that holds quarks together, aptly named the strong nuclear force, behaves unlike any other force we know. It acts like a cosmic rubber band. When 2 quarks are close together, the force is relatively weak. But as you try to pull them apart, the force gets stronger and stronger, exponentially so. If you pour enough energy into a proton to try and rip one of its quarks out, that energy will simply snap the rubber band, and the energy itself will spontaneously convert into a brand new pair of quarks, which immediately bind to the ones you were trying to separate. You don't end up with a free quark, you end up with a whole new particle. It's a cosmic rule that seems impossible to break. What other unbreakable rule of physics fascinates you the most? Drop your thoughts in the comments below. Quarks, however, only make up 1/2 of the family of fundamental matter. Their siblings are a group of particles called leptons, and you're already very familiar with one of them, the electron. Like quarks, leptons are thought to be truly fundamental points with no internal structure. And just like quarks,
They come in different generations of increasing mass. The electron has two heavier, unstable cousins, the muon, which is about 200 times more massive, and the tau, which is a whopping 3,500 times more massive. But the most mysterious leptons are the neutrinos. There are three types, one corresponding to each of the other leptons. Neutrinos are fantastically strange.
They are so light and interact so weakly with other matter that trillions of them, created by the sun, are streaming through your body every single second, passing through you, the chair you're sitting on, and the entire planet as if it were all empty glass. So we have our matter particles, 6 quarks and 6 leptons, but that's not the full picture. For matter to do anything, to stick together, to repel, to decay, it needs forces. And in the quantum world, forces aren't some mysterious pull. They are actually carried by other particles. These force-carrying particles are called bosons. When you see light, you're actually seeing a stream of photons, the bosons that carry the electromagnetic force. The strong nuclear force, the one gluing quarks together inside protons and neutrons with that unbreakable rubber band, is carried by a boson called the gluon. And the weak nuclear force, which is responsible for certain types of radioactive decay, is carried by 2 particles known as the W and Z bosons. Every interaction, every push and pull at the deepest level is just matter particles tossing these force-carrying bosons back and forth. This beautiful, intricate system of 12 matter particles and 4 force particles, known as the Standard Model of Particle Physics, can describe almost every physical interaction we've ever observed. But for years, it had a gaping hole in it. The model worked perfectly, but it could only do so if all these fundamental particles had 0 mass, which they clearly don't. An electron has mass. A top quark is incredibly heavy. Something was missing. The solution was a final, crucial puzzle piece, the Higgs boson. The theory proposed that the entire universe is permeated by an invisible energy field, the Higgs field. As fundamental particles travel through this field, they interact with it. The more a particle interacts, the more it gets bogged down. And this drag is what we perceive as mass. Particles like the photon don't interact with the field at all, so they remain massless and travel at the speed of light. But a particle like the top quark interacts with it intensely, making it the heaviest fundamental particle ever discovered. The Higgs boson, then, is a bundled-up excitation of this field, proof that the mass-giving mechanism is real. After a nearly 50-year search, its discovery in 2012 was a monumental triumph, the capstone on our incredible theory of matter. And yet, this beautiful model still can't explain everything. It says nothing about gravity, and it has no answer for the biggest mysteries of all, like the dark matter that holds our galaxies together, a mystery we are getting ever closer to unraveling. Imagine a clock that ticks slower the faster you move. Now imagine another clock that speeds up the higher you climb. These aren't props from a fantasy film. They are real clocks, and you are living in their world every single second. Time isn't the steady, universal river we imagine it to be. It's a tangled, elastic, and mind-bending dimension of reality, and we're about to dive into its deepest and strangest currents. You might want to sit down for this, because according to Einstein, your head is aging faster than your feet, right now. It's an infinitesimally small difference, but it is real. This is called gravitational time dilation. Einstein's theory of general relativity tells us that gravity is a curvature in the fabric of space-time, and massive objects bend this fabric. The stronger the gravity, the deeper the curve, the slower time flows. Since your feet are closer to the center of Earth's massive gravity well, time for them is ticking just a fraction of a second slower than it is for your head. This isn't just a quirky thought experiment, it's a critical component of modern technology.
The GPS satellites orbiting our planet are in a region of weaker gravity, so their internal clocks run faster than ours on the ground. They also move incredibly fast, which has a separate, slowing effect on their time. If engineers didn't constantly correct for both of these relativistic effects, the entire GPS system would fail, accumulating errors of several kilometers every single day. Your phone's map works because it understands that time itself is flexible. That same flexibility doesn't just apply to gravity, it's also tied to your speed. As you move through space, you change how you move through time. This is the core of special relativity. The faster you travel through the 3 dimensions of space, the slower you travel through the 4th dimension, time, relative to a stationary observer. If you were to board a spaceship and travel at 99.9% the speed of light for just 5 years, you would return to Earth to find that over a century had passed. Your friends, your family, everyone you knew would be long gone. You would have effectively traveled into the future. This isn't science fiction. It is a fundamental consequence of the structure of our universe. Every time you're in a car, a train, or a plane, your personal clock is ticking ever so slightly slower than the clocks of people standing still. The universe doesn't have a master clock. Every single object carries its own. This leads to one of the most reality-shattering consequences of physics. There is no such thing as a universal now. The idea that we all share a single, simultaneous present moment across the cosmos is an illusion. Imagine 2 lightning bolts striking the front and back of a moving train at the same time from the perspective of a person standing on the platform. To them, the events are simultaneous. But for someone in the middle of that train, the light from the front strike will reach them before the light from the back strike because they are moving towards the front event. For them, the lightning at the front of the train genuinely happened first. The shocking part is that both observers are correct in their own frame of reference. Simultaneity is relative. This means a hypothetical alien civilization a million light years away doesn't exist right now in any absolute sense. Depending on your motion, their now could be our distant past or our far future. If you could freeze the entire universe for what you perceive as 1 second, what would you most want to see? Let me know your thoughts down in the comments. So, if now is slippery, what about the flow from past to future? Why does time seem to move in only one direction? We remember yesterday, but not tomorrow. A broken egg never unscrambles itself. This one-way street is known as the arrow of time, and strangely, most fundamental laws of physics, from gravity to electromagnetism, are time-symmetric. They would work perfectly fine in reverse. The real reason for time's arrow comes from something called entropy. The second law of thermodynamics states that in an isolated system, disorder, or entropy, always increases. The universe began in a very hot, dense, and highly ordered state. Ever since the Big Bang, it has been expanding, cooling, and becoming more disordered. Stars burn out, energy spreads, and structures decay. The reason you can't unbreak an egg is because a scrambled egg is a vastly more disordered state than a whole one. Time moves forward because the universe as a whole is moving towards a state of maximum chaos. It's the universe's unstoppable slide into disorder that paints the forward direction on our perception of reality. This arrow of time unfolds on the grandest cosmic scale, but what about the smallest? Is there a minimum unit of time? A single frame of the universal movie? Physics says yes. It's called Planck time. It is the shortest possible meaningful interval of time, calculated to be about 10 to the power of -43 seconds. It is a duration so incomprehensibly brief that there are more units of Planck time in a single second than there have been seconds since the Big Bang. It's the time it would take a photon traveling at the ultimate speed of light to cross the smallest possible distance, the Planck length. Below this fundamental limit, our current understanding of physics completely breaks down.
The concepts of time and space as we know them dissolve into a quantum foam where cause and effect lose their meaning. Time doesn't flow smoothly. It ticks by in these impossibly tiny, discrete steps. At these infinitesimal scales, the rules of reality become so bizarre they can almost seem like magic. Consider quantum tunneling. In our classical world, if you throw a ball at a wall, it will either bounce off or, if you throw it hard enough, break through. It can't just appear on the other side. But in the quantum realm, particles can and do. A particle can face a barrier it doesn't have enough energy to overcome and still have a probability of just appearing on the other side, as if it tunneled through an impassable wall. This isn't just a theoretical quirk, it's the reason our sun shines. The pressure and temperature at the sun's core aren't quite high enough for atomic nuclei to overcome their mutual repulsion and fuse. They get close, but the final leap is made possible by tunneling through that final energy barrier. This process, so vital for life on Earth, operates on timescales that defy classical intuition, a constant reminder that at its most fundamental level, reality doesn't play by our rules. And perhaps most personally, this stretching and shrinking of time isn't just a feature of the cosmos, it's a feature of our own minds. While the laws of physics don't change, our perception of them certainly does. You've likely heard stories of people in car accidents or life-threatening situations experiencing time slowing down, allowing them to perceive events in extreme detail. This isn't a paranormal event, it's a neurological one. During moments of intense fear, the amygdala, your brain's threat detection center, kicks into overdrive. It begins recording memories with a much higher density of information than usual. When you later recall that event, your brain has so many more frames to process that it feels as though the moment stretched out over a longer period. Time didn't actually slow down, but your brain created a high-definition, slow-motion replay of reality. It's a powerful demonstration that our experience of time is not a pure reflection of the outside world, but a complex construction of physics, biology, and consciousness, forever dancing together across the fabric of space-time. Imagine for a moment you're a skydiver, plummeting toward the Earth. What's pulling you down? Gravity, right? But what stops you from becoming a permanent part of the pavement? It's not the ground itself. It's an invisible force field, a trillion times stronger than the one pulling you down. Every moment of your life is a constant, silent war between the fundamental forces that sculpt our reality, from the inside of an atom to the edge of the cosmos, and you're caught right in the middle. Let's explore the titans of physics that govern everything. We all think we know gravity. It's the ultimate cosmic anchor, holding planets in orbit and keeping our feet on the ground. But here's something that will change how you see it forever. Gravity is astonishingly, almost comically weak. It is by far the wimpiest of the four fundamental forces. How weak? You can prove it right now. Pick up a paperclip with a tiny refrigerator magnet. That little magnet is defeating the entire gravitational pull of a 6 trillion kilogram planet. The electromagnetic force in that magnet is overwhelmingly more powerful than the gravity of the whole Earth. If gravity were even a little bit stronger, stars would burn out in an instant, and the universe as we know it would collapse before it even began. Its perfect weakness is the secret ingredient for a long-lived, stable cosmos. So, if gravity is this feeble cosmic force, how does it manage to build galaxies? The secret is that it's not really a force in the way we usually think about it. Albert Einstein's theory of general relativity revealed that gravity isn't a pull, but a push from space-time itself. Massive objects don't pull on other objects, they bend the very fabric of space and time around them. Imagine a bowling ball on a trampoline. It creates a deep well in the fabric.
A marble rolled nearby will fall into that well, not because the bowling ball is pulling it, but because the shape of the fabric is guiding its path. That's gravity. You aren't being pulled to the Earth. The warped space-time around Earth is continuously pushing you toward its surface. Every orbit, every falling apple, is just an object following the straightest possible path through a curved, four-dimensional universe. Now, let's talk about the force that stopped our hypothetical skydiver, the one that makes solid matter feel, well, solid. The electromagnetic force. It's the force responsible for light, electricity, magnetism, and nearly all of the chemistry that makes life possible. When you clap your hands, the feeling of impact isn't your skin atoms actually touching. It's the colossal repulsion between the electron clouds of the atoms in one hand and the electron clouds in the other. This force is what holds molecules together, allowing for everything from water to DNA. It's so powerful that the electromagnetic repulsion between two protons is about 10 to the 36 times stronger than their gravitational attraction. That's a 1 followed by 36 zeros. Essentially, everything you interact with in your daily life that isn't gravity is, in some form, electromagnetism. We think of it creating lightning or powering our homes, but it's working at a much deeper, more fundamental level all the time. What's the most powerful display of electromagnetism you've ever seen in nature? Let me know your thoughts down below. This force's power creates a huge problem, though, when you zoom into the heart of an atom. The nucleus of an atom is crammed full of positively charged protons. Based on the rules of electromagnetism, these protons should repel each other with unimaginable force, blowing the nucleus apart instantly. So why doesn't all matter just disintegrate? Because the universe has a secret weapon, the strong nuclear force. This is the universe's ultimate superglue. It's about 137 times stronger than electromagnetism, but it operates over an incredibly tiny distance, only about the width of a proton. If you can get two protons close enough, the strong force will suddenly grab hold and bind them together, completely overwhelming their electromagnetic desire to fly apart. It's this force that fuses elements in the cores of stars and keeps the building blocks of our world from violently exploding. But the strong force does something even more profound, something that might be one of the most shocking facts in all of physics. It's responsible for creating almost all of your mass. You might have heard that the Higgs field gives particles mass, and that's true for fundamental particles like quarks and electrons. But the quarks that make up the protons and neutrons in your body only account for about 1% of your total mass. Where does the other 99% come from? It comes from pure energy. According to Einstein's famous equation, E equals mc squared, energy and mass are two sides of the same coin. The strong nuclear force binds quarks together with such immense energy that this binding energy itself manifests as the majority of the mass of protons and neutrons, and therefore the mass of you, me, and everything we can see. You are not mostly star stuff, you are mostly concentrated nuclear energy. Now, for the last, and perhaps strangest of the four forces, the weak nuclear force. While the strong force is the universe's glue, the weak force is the agent of change. It's the only force capable of changing one type of subatomic particle into another. For instance, it can flip a neutron into a proton, or vice versa. This might sound obscure, but without it, the universe would be a dark and lifeless place. The sun shines because the weak force allows hydrogen nuclei to transform and fuse into helium, releasing enormous amounts of energy. It's also the force behind most forms of radioactive decay, the process that allows archaeologists to carbon date ancient artifacts and geologists to determine the age of the Earth. It's weaker than both the strong and electromagnetic forces, and like the strong force, its range is incredibly short. But its ability to fundamentally alter the identity of particles makes it a crucial player in the cosmic story.
These four forces, gravity, electromagnetism, the strong and the weak, seem so different, a motley crew governing the universe on vastly different scales with wildly different strengths. And yet, physicists believe that this wasn't always the case.
In the first fiery moments after the Big Bang, when the universe was trillions of degrees hotter than it is today, these four distinct forces were actually one. They were all merged into a single, unified superforce. As the universe expanded and cooled in the fractions of a second after its birth, this unified force froze out or separated one by one into the distinct interactions we observe today, much like steam condenses into water and then freezes into ice. Physicists are still searching for a grand unified theory that can mathematically describe this primordial state, to find the single equation that gave birth to the forces that now shape everything, from a single unified power to the four architects of our reality. But how do these forces actually talk to each other? The answer involves some of the strangest particles in the entire universe. Imagine a star torn from its home and violently flung into the abyss between galaxies. This isn't science fiction. This is the reality for hypervelocity stars. Our own galaxy's supermassive black hole, Sagittarius A star, acts as a colossal gravitational slingshot. When a binary star system strays too close, the black hole can capture one star while ejecting the other at unimaginable speeds. We're talking about velocities over 1.5 million kilometers per hour, fast enough to escape the Milky Way's gravitational pull entirely. These stellar exiles are doomed to wander the lonely, dark void of intergalactic space for eternity, a solitary point of light on a journey to nowhere. They are a stark reminder that even on the grandest scales, the universe is a place of violent and sudden change, a cosmic billiard table where even suns can be knocked right off the board. From stars being thrown into the void, let's journey to a place that is the void. If you were to travel through the universe, you'd see galaxies clustered together in long filaments, separated by vast, dark regions, like a cosmic web. But there's one region that defies all expectations, the Bootis Void. It is an immense, almost perfectly spherical region of space, nearly 330 million light-years in diameter, that is profoundly empty. While you'd expect a region this size to contain thousands of galaxies, astronomers have only found about 60. It's so desolate that if our Milky Way were at its center, we wouldn't have known other galaxies existed until the 1960s. Its existence challenges our models of how the universe formed. Such a colossal pocket of nothingness shouldn't have had time to form since the Big Bang. What cosmic process could have scooped out a section of the universe this large? Let me know in the comments. If you could give this vast, lonely place a nickname, what would it be? Now, let's swing the pendulum from cosmic emptiness to an object of almost unimaginable density and power, a magnetar. A magnetar is a type of neutron star, the crushed core left behind after a massive star goes supernova. But it's a neutron star with a twist. It possesses a magnetic field so powerful it's almost impossible to describe. Earth's magnetic field protects us from solar wind. A refrigerator magnet can hold up a drawing. A magnetar's field is a quadrillion times stronger than Earth's. If you were within 1,000 kilometers of one, its magnetic field would distort your atoms, literally tearing you apart molecule by molecule. This magnetic field is so intense that it causes the star's crust to crack and shift, creating starquakes. These quakes release more energy in 1/10 of a second than our sun has radiated in the last 100,000 years.
blasting out gamma rays and X-rays that can be detected clear across the galaxy. That kind of stellar pressure is immense, but a different kind of pressure creates our next oddity, something that completely breaks our Earth-based intuition. Imagine a world where the oceans are boiling, but the water is frozen solid. Welcome to planets like Gliese 436b, a potential hot ice world. The planet orbits so close to its star that its surface temperature is over 400 degrees Celsius, hot enough to melt lead. Yet, its massive gravity creates such extreme atmospheric pressure that the water molecules are crushed together with incredible force. This pressure is so great that it overrides the thermal energy of the heat, forcing the water to become a solid. This isn't the ice we know, but a bizarre, exotic form of solid water called Ice 7 or Ice 10. You could stand on a block of ice that is simultaneously hundreds of degrees hot. It's a world built from a substance that shouldn't exist, a planet of burning ice. This idea of matter behaving in ways that defy our normal perception is at the very heart of physics. For centuries, we've known about crystals, materials whose atoms are arranged in a repeating pattern in space, like the lattice of a diamond or a snowflake. But what if a pattern could repeat not in space, but in time? That's the mind-bending concept of a time crystal. First proposed in 2012 and now created in labs, a time crystal is a new phase of matter. In its lowest energy state, where all motion should cease, its constituent particles continue to move, oscillating or flipping in a repeating pattern forever without using any energy. It's like a clock that runs eternally without a battery. This breaks a fundamental symmetry of physics called time translation symmetry and opens the door to new quantum technologies and a deeper understanding of reality itself, proving that the universe still has fundamental states of being that we are only just beginning to discover. From the impossibly small to the incomprehensibly large, our own cosmic neighborhood has a mystery that affects us directly. Our Milky Way galaxy, along with the Andromeda galaxy and the entire Virgo supercluster containing thousands of other galaxies, is being pulled. We are all hurtling through space at over 2 million kilometers per hour towards a single, unseen point in the cosmos. We call it the Great Attractor. This gravitational anomaly is a massive concentration of matter equivalent to tens of thousands of galaxies, but we can't see it clearly. It lies in a direction obscured by the dense plane of our own Milky Way, a region called the Zone of Avoidance. We know it's there only by its gravitational influence, a cosmic river pulling everything towards it. We don't know what it is, a gargantuan supercluster, a strange filament of dark matter, or something else entirely. But one thing is for certain, our galaxy is on a one-way trip, pulled by an invisible force towards a destination we cannot see. Have you ever felt a spark of static electricity? That tiny shock is a fleeting glimpse into a cosmic rulebook that governs everything from the flicker of a candle to the explosion of a star. We think of energy as something we use up, something that runs out. But the universe has a secret. Energy is never, ever lost. It just changes its costume. Today, we're peeling back the curtain on these endless transformations, revealing the fundamental laws that keep our reality in motion. Let's start with a simple act, dropping a ball. As it falls, it picks up speed. This is a classic example of potential energy, the energy of position, converting into kinetic energy, the energy of motion. But when it hits the ground and bounces, it never quite reaches the same height it started from. So where did the energy go? It wasn't destroyed. Instead, it embarked on a spectacular series of transformations. A portion of it became thermal energy, slightly heating the ball and the floor upon impact. Another piece transformed into sound energy.
That distinct thump you hear is literally the kinetic energy being broadcast through the air as pressure waves. A tiny fraction was even used to momentarily deform the shape of the ball itself. If you could meticulously measure the heat, the sound, and the energy of the now lower bounce, you would find that every single joule of the original potential energy is accounted for. This is the first law of thermodynamics in action, the law of conservation of energy. It is perhaps the most absolute and unbroken rule in all of physics. No process has ever been observed to violate it. Every single unit of energy that existed at the Big Bang is still present in the cosmos today, just endlessly changing form, from the light of a distant galaxy to the chemical energy in the food you eat. So, if energy is always conserved, why can't we unbreak an egg or unmelt an ice cube? If all the energy is still there, why can't processes just run in reverse? The answer lies in one of the most profound and misunderstood concepts in all of science: entropy. This is the second law of thermodynamics, and it essentially states that in any isolated system, the amount of disorder, or entropy, will always tend to increase over time. Think of a hot cup of coffee left in a room. The heat energy in the coffee is highly concentrated. Over time, that energy naturally spreads out into the cooler air of the room, warming it up slightly until the coffee and the room are the same temperature. The total energy is conserved, but it has gone from an ordered state, hot coffee, cool room, to a disordered one, lukewarm coffee, lukewarm room. The energy has dissipated. This universal, one-way trend towards disorder is what gives time its arrow. The reason you remember the past, but not the future, is because the universe is constantly moving towards a state of higher entropy. You can't unbreak the egg, because that would require countless scattered particles to spontaneously reassemble into a more ordered state, a statistical impossibility of such epic proportions that it would simply never happen. Every moment of your life is a ride on the relentless, forward-moving wave of increasing entropy. Now let's take this idea of energy transformation to the most extreme powerhouse we know, our sun. The light and heat that reach us from 93 million miles away are not the result of a simple fire. The sun isn't burning in any chemical sense. It's a colossal nuclear furnace running on Einstein's famous equation, E equals mc squared. In the crushing pressure and unimaginable heat of its core, the sun is fusing hydrogen atoms together to create helium. But here's the magic. The resulting helium atom has slightly less mass than the individual hydrogen atoms that formed it. This missing mass hasn't vanished. It has been converted directly into a pure, explosive burst of energy. Every single second, the sun converts about 4 million tons of its own matter into energy. Let that sink in. Not 4 million tons of fuel, but 4 million tons of its very substance, annihilated and reborn as the light that makes life on Earth possible. This is the ultimate energy transformation, turning the fabric of matter itself into the radiation that floods our solar system. But the sun's energy, and indeed the energy of all the stars and matter we can see, is just a tiny fraction of what's really out there. Astronomers in the late 1990s were trying to measure how much the universe's expansion was slowing down due to gravity. They expected to see a deceleration. Instead, to their complete astonishment, they found the exact opposite. The expansion of the universe is accelerating. It's speeding up, with galaxies flying away from each other faster and faster over time. To explain this, physicists have proposed the existence of one of the most mysterious substances imaginable: dark energy. This isn't energy in the way we typically think of it. It appears to be a property of space-time itself, a kind of anti-gravity that pushes everything apart. Current models suggest that a staggering 68% of the entire energy mass content of the universe is dark energy.
We can't see it, we can't touch it, and we have almost no idea what it is. Yet it is the dominant force shaping the ultimate fate of our cosmos. What do you think dark energy could be? Let me know your most creative theories down in the comments. From the cosmic and mysterious, let's bring it back to the familiar and miraculous. Every green leaf on every tree is a sophisticated energy conversion factory. The process of photosynthesis is a masterclass in turning one form of energy into another, and it's the foundation of nearly all life on Earth. A plant absorbs photons, particles of light energy that have traveled from the sun. It then uses this solar energy to power a complex chemical reaction, breaking apart water and carbon dioxide molecules and rearranging them into glucose, a sugar molecule. In doing so, it converts electromagnetic energy from the sun into stable, storable chemical energy. This chemical energy is what fuels the plant's growth, and it's the same energy that gets passed up the food chain when an animal eats the plant. What's truly remarkable is the efficiency of this process at the quantum level. The plant is able to channel the energy of a captured photon with almost perfect precision to the exact molecular machinery that needs it, a feat of natural engineering that our best solar panels are still struggling to replicate. Finally, we arrive at the strangest transformation of all, getting something from nothing. Imagine two perfectly flat, uncharged metal plates placed incredibly close together in a perfect vacuum. You'd expect nothing to happen, but something does. A real, measurable force pushes the plates together. This is the Casimir effect, and it's proof that a vacuum is not truly empty. According to quantum field theory, empty space is actually a roiling sea of potential, with pairs of virtual particles and antiparticles popping into existence and annihilating each other in fractions of a second. Normally, this energy foam is all around us. But the tiny gap between the two plates restricts the kinds of virtual particles that can appear there. Only particles with wavelengths that fit perfectly into the gap are permitted. The space outside the plates, however, has no such restrictions. This means there is more quantum pushing on the outside of the plates than on the inside, creating a net force that squeezes them together. This is a physical force, a form of energy generated not from matter, but from the very structure of the void. It's a profound reminder that even in the most absolute emptiness we can imagine, the universe's endless dance of energy continues. What if I told you the universe is not just expanding, but that our entire galaxy and 100,000 others are being dragged sideways through space at 2 million kilometers per hour by something we can't even see? That's not a hypothetical. That's our reality. We're on a cosmic journey into the deepest, strangest, and most magnificent frontiers of physics. If you believe the universe is the ultimate mystery, then hit that subscribe button, because we're about to unravel some of its greatest secrets. Our journey begins with that mysterious pull. For decades, astronomers noticed that everything in our cosmic neighborhood, the Milky Way included, was streaming toward a specific point in the constellation Centaurus. The cause is a gravitational anomaly so massive, it's been dubbed the Great Attractor. This isn't just a big cluster of galaxies, it's a concentration of mass equivalent to quadrillions of suns, exerting a relentless gravitational tug on a region of space hundreds of millions of light years across. The craziest part? We can't get a clear look at it. It's hidden behind the zone of avoidance, the dense plane of our own Milky Way galaxy, which is filled with so much gas and dust that it blocks our view like a thick fog. We know this cosmic titan is there because we can feel its pull, like an invisible cosmic tide, dragging us and our galactic neighbors toward an unknown fate. From the incomprehensibly large to the impossibly dense, let's talk about the cosmic relics left behind when giant stars die, neutron stars. When a star many times the mass of our Sun collapses, it crushes its protons and electrons together to form neutrons, packing more mass than our entire Sun into a sphere just 20 kilometers across. The result is an object with a gravitational field so intense that if you dropped something from 1 meter above its surface, it would hit at over 7 million kilometers per hour. A single teaspoon of neutron star material would weigh about 6 billion tons, more than all of humanity combined. Many of these stars spin hundreds of times per second, sweeping beams of radiation through space like a lighthouse, which we observe as pulsars. And the most extreme kind, magnetars, possess magnetic fields a quadrillion times stronger than Earth's, so powerful they could wipe every credit card on the planet from halfway to the moon. Now, let's flip that idea of extreme density completely on its head. From one of the most crowded objects in the universe, we travel to one of the loneliest places imaginable, the Boutte's Void. Discovered in 1981, this is a colossal, spherically shaped region of space that is almost entirely empty. It's so vast, at nearly 330 million light-years in diameter, that if our Milky Way were at its center, our nearest galactic neighbor wouldn't be seen until we were almost at the edge. To put its emptiness in perspective, a region of space this large should contain thousands of galaxies, yet astronomers have only found about 60. It's a profound cosmic desert, a void so vast and barren it's been nicknamed the Great Nothing. The sheer existence of such an empty expanse challenges our models of how the universe formed on a grand scale. If you could give an official name to a massive void in space, what would you call it? Let me know your most creative cosmic names in the comments below. So, with these vast empty spaces separating everything, how do we possibly see the most distant objects at the edge of the observable universe? Well, physics gives us a cheat code. Albert Einstein predicted that gravity isn't a force, but a curvature in the fabric of space-time itself. This means that incredibly massive objects, like galaxies or galaxy clusters, can actually bend the light that travels past them from more distant objects. This phenomenon is called gravitational lensing. It essentially turns these massive structures into natural, cosmic magnifying glasses. Sometimes, this lensing effect smears the light of a distant galaxy into a beautiful arc or a complete circle known as an Einstein ring. Other times, it can create multiple images of the same object, like the famous Einstein cross, where we see 4 distinct images of a single distant quasar. Thanks to this cosmic trick of the light, we can study galaxies that would otherwise be too far away and too faint to ever detect. Speaking of things that are hard to detect, let's consider the lonely wanderers of the cosmos. We tend to think of planets as being cozily tethered to a parent star, but the universe is teeming with rogue planets. These are worlds that have been ejected from their original solar systems and now drift alone through the cold, dark expanse of interstellar space. They are unbound, starless nomads. Current estimates suggest there could be billions or even trillions of these orphan planets in our Milky Way alone, potentially outnumbering the stars themselves. Without a star for warmth, their surfaces would be frozen, but it's possible that larger, gas giant-sized rogues could retain enough internal heat from their formation to harbor liquid water oceans under thick, insulating atmospheres or icy shells. What do you think life would be like on a planet with no sun, just the faint light of distant stars? Share your most imaginative sci-fi ideas in the comments. From the darkest objects to the oldest light, it turns out that deep space isn't completely black. If you had a radio telescope for eyes, you'd see a faint, uniform glow coming from every single direction you looked. This is the cosmic microwave background, or CMB. It is, quite literally, the afterglow of the Big Bang. This is the oldest light in the universe. radiation that was released just 380,000 years after creation, when the universe cooled enough for atoms to form and light could finally travel freely. It's effectively the universe's baby picture. And encoded within this ancient light are tiny, almost imperceptible temperature fluctuations. These minuscule hot and cold spots represent the very first seeds of structure, the quantum fluctuations that were stretched across the cosmos and eventually grew into the galaxies, stars, and voids we see today. If you could send a single message back in time to be imprinted on the cosmic microwave background for a future civilization to find, what would it say? Drop your profound, universe-altering thoughts below. From the universe's first breath, we now look to its very last. The ultimate fate of everything is one of the biggest open questions in cosmology, and it hinges on the mysterious force known as dark energy. This is the stuff that's causing the expansion of the universe to accelerate. Depending on its true nature, one of several scenarios could play out. The leading theory is the heat death, or big freeze. In this future, the expansion continues forever. Galaxies will drift so far apart they disappear from each other's view. Stars will burn out, matter will decay, and the universe will become a cold, dark, and empty place of low-energy particles. Another, more violent possibility is the Big Rip, where dark energy becomes so strong it overcomes gravity, tearing apart galaxies, stars, and eventually atoms themselves. A less likely alternative is the Big Crunch, where the expansion eventually reverses and the universe collapses back in on itself, potentially leading to a new Big Bang. We've journeyed from a mysterious pull on our galaxy to the echoes of creation itself and peered into the possible ends of time. The deep cosmos shows us that reality is grander, stranger, and more beautiful than we could ever imagine. If these cosmic chronicles expanded your mind, do me a favor and hit that like button. And be sure to subscribe, because next time we're flipping the script entirely. We're going from the biggest things in the universe to the smallest, entering a realm where particles can be in two places at once, and reality itself gets weird. You won't want to miss it. That phone in your pocket, the one you use to navigate across town? It's constantly listening to whispers from the edge of space-time, proving Einstein right every single second. Physics isn't just about black holes and distant galaxies, it's the hidden instruction manual for your entire world, and we're about to read some of its most surprising pages. If you enjoy having your mind blown by the reality hiding in plain sight, do us a favor and hit that like button and subscribe for more. Now, let's get into it. Your global positioning system, or GPS, would be completely useless without Albert Einstein's theories of relativity. It's not a minor adjustment, it's fundamental. The system works by triangulating your position from satellites orbiting Earth, each carrying an incredibly precise atomic clock. But here's the twist. Due to special relativity, because those satellites are moving so fast relative to you on the ground, their clocks actually tick slightly slower. But wait, it gets weirder. General relativity also comes into play. Because the satellites are in a weaker gravitational field far above the Earth's surface, their clocks actually tick faster than ours. It turns out the effect from general relativity is much stronger than the effect from special relativity. The result is that clocks on GPS satellites gain about 38 microseconds every single day compared to clocks on Earth. It sounds insignificant, right? But if engineers didn't constantly correct for this relativistic time warp, navigation errors would accumulate at a rate of about 10 kilometers every single day. Within minutes, your GPS would send you into a lake. Every time you open your map app, you are using a practical, everyday application of one of the most profound theories about the nature of reality itself. But you don't need a billion-dollar satellite network to witness the universe's fundamental constants at work. You can actually measure the speed of light in your own kitchen using a microwave, a ruler, and a bar of chocolate. When you take the rotating plate out of your microwave and heat a stationary chocolate bar for a short time, you'll notice it doesn't melt evenly. Instead, you'll get a few specific melted spots. This is because microwaves cook food using standing waves of energy. The melted spots are the hot spots, or antinodes, of these waves. The distance between two of these melted spots is half the wavelength of the microwaves. If you measure that distance in centimeters, multiply it by 2 to get the full wavelength, and then multiply that by the frequency of your microwave oven, which is printed on a label on the back, usually around 2450 megahertz, you will calculate the speed of light. Your answer will be astonishingly close to the actual value of nearly 300,000 kilometers per second. You've just used a kitchen appliance and a sweet treat to measure a cosmic speed limit. What's the coolest home science experiment you've ever tried? Let me know down in the comments. Speaking of bizarre kitchen physics, consider this paradox that has stumped scientists for centuries. Under certain conditions, hot water can actually freeze faster than cold water. This is known as the Mpemba effect, named after a Tanzanian student who observed it while making ice cream in the 1960s, though the phenomenon had been noted by thinkers as far back as Aristotle. It completely defies intuition. You'd think the colder water has a head start, so it should always win the race to freeze. But countless experiments have confirmed it's a real phenomenon.
Scientists still debate the exact cause, with leading theories suggesting that hotter water evaporates more quickly, reducing the total volume that needs to freeze, or that it has fewer dissolved gases, which can alter the freezing point, or that convection currents in the hotter water promote faster heat transfer. It's a powerful reminder that even the simplest, most familiar processes in our world can hold deep and complex mysteries. Water isn't the only common substance with a shocking secret. Sometimes, just walking across a carpet on a dry day can turn you into a human capacitor, storing up a surprising amount of electrical charge. When you then reach for a metal doorknob, you get that familiar zap of static electricity. That tiny spark is, for all intents and purposes, a miniature lightning bolt. As you scuffed your feet, you scraped off billions, even trillions of electrons, creating a massive electrical imbalance in your body. The doorknob, being a conductor, offers a path for that excess charge to escape. That visible spark you see is the air itself being superheated and ionized as a torrent of trillions of electrons makes the jump from your fingertip to the metal. You're not just getting a little shock, you are witnessing a colossal migration of subatomic particles powerful enough to bridge an air gap. Have you ever gotten a really surprisingly big static shock? I want to hear the story. While that static spark is chaotic and jagged, other everyday phenomena are models of perfect, elegant efficiency. Take the humble soap bubble. When you blow a bubble, it will always, without fail, form a perfect sphere. This isn't a coincidence, it's a profound law of physics in action. A sphere is the unique mathematical shape that encloses the most volume with the least possible surface area. The surface tension of the soapy water acts like an elastic skin, constantly pulling inward to minimize its own area. For a trapped pocket of air, the most energy-efficient, lowest stress shape it can possibly form is a sphere. The bubble isn't choosing to be round, it's simply settling into the lowest energy state possible. It's nature's ultimate minimalist design, a beautiful and fragile demonstration of energy conservation playing out in your backyard. This feels like a good moment to ask, what's the most beautiful natural pattern you've ever seen? And that same principle of efficiency leads us from something as fragile as a bubble to one of the strongest materials ever discovered. And you almost certainly have some sitting on your desk. The lead in your pencil isn't lead at all, it's a form of carbon called graphite.
What's amazing is that graphite is made of countless layers of carbon atoms arranged in a hexagonal, chicken wire-like pattern. A single, one-atom-thick sheet of this material is called graphene. Discovered properly in 2004, a feat that won the Nobel Prize, graphene is over 200 times stronger than steel by weight, incredibly light, flexible, and a superb conductor of heat and electricity. Every single time you draw a line with a pencil, the graphite sheds layers. You are quite literally exfoliating microscopic, sometimes single-atom-thick sheets of a supermaterial onto the paper. The everyday act of writing is an act of creating infinitesimal amounts of one of the most revolutionary substances of the 21st century. From super strong carbon, let's head back to the kitchen one last time to a device that cooks your breakfast with invisible fire. When you put a slice of bread in a toaster, you might assume it's the hot air inside that does the cooking. But that's not the main story. The real work is done by the glowing red-hot wires you see inside. Those wires are emitting intense waves of infrared radiation. Infrared is a form of light or electromagnetic radiation, but with a wavelength too long for our eyes to see. We perceive it as heat. This invisible light travels through the air and is absorbed directly by the water and organic molecules in the bread, causing them to vibrate rapidly and heat up. Your toaster isn't just a hotbox, it's a radiation emitter that is literally painting your bread with a specific frequency of light, perfectly tuned to brown it into a delicious slice of toast. Simple question for the comments: toast, bagel, or English muffin? The physics of breakfast demands an answer. From your phone's connection to relativity, to the invisible light in your toaster, the fundamental laws of the universe are not distant concepts. They are here, shaping every moment of your day in the most extraordinary ways. If you found the physics of your kitchen as fascinating as we do, show your support by hitting that like button and make sure you're subscribed with notifications on so you don't miss the next chapter of our journey. Everything you can see, every star, every galaxy, every planet, and every person makes up less than 5% of the entire universe. The rest? It's a vast, invisible cosmos that surrounds us, pulls on us, and dictates our ultimate fate. We're about to pull back the curtain on the other 95%. The story of this invisible universe really begins with a mystery of impossible speed. Back in the 1930s, an astronomer named Fritz Zwicky was observing the Coma Cluster, a sprawling city of galaxies. He calculated the mass of all the visible stars and gas within it, and then measured how fast the outer galaxies were orbiting the cluster's center. The numbers didn't add up, not even close. The galaxies were moving so incredibly fast that the gravity from the visible matter should have been far too weak to hold on to them. The entire cluster should have flung itself apart millions of years ago. Zwicky realized there had to be something else there, a huge amount of unseen mass providing the extra gravitational glue. He called it dunkle Materie, or dark matter. For decades, it was a fringe idea, but the evidence kept piling up, confirming that galaxies are all nested within massive, invisible halos of this mysterious substance. But when we say dark matter, it's a bit of a misnomer. It's not dark like a black hole or a lump of coal. It's not something that absorbs light or casts a shadow. The truth is far stranger. Dark matter is completely, utterly transparent. It doesn't interact with light or any form of electromagnetic radiation in any way. It doesn't absorb it, it doesn't reflect it, and it doesn't emit it. A light beam would pass straight through a giant clump of dark matter as if nothing were there. It also doesn't interact with normal matter, except through the gentle, persistent tug of gravity. This is why you can't touch it, see it, or feel it, even though it outweighs all the normal matter in the universe by more than 5 to 1. It's a ghostly sea of substance that our senses and our instruments are almost completely blind to.
So if we can't see it or touch it, how can we be so sure it's there? We watch for its gravitational footprint, and one of the most powerful tools for this is a phenomenon predicted by Einstein himself: gravitational lensing. Imagine a massive, invisible ball of dark matter sitting in space between us and a distant galaxy. Just as a glass lens bends light, the immense gravity of the dark matter halo bends the fabric of space-time around it. Light from the distant galaxy travels towards us, but as it passes by the dark matter, its path is warped. From our perspective on Earth, we see the background galaxy as distorted, smeared, or even multiplied into several images, forming beautiful arcs and rings of light. By analyzing these distortions, astronomers can create a map of where the invisible matter is hiding, revealing the unseen structures that dominate our universe. It's like seeing the silhouette of an invisible person by observing how they warp the light passing behind them. The most precise picture of this invisible cosmos comes not from looking at galaxies, but from studying the faintest, oldest light in the universe. This is the cosmic microwave background, or CMB, the leftover heat from the Big Bang. It's a faint glow of radiation that fills all of space, and it's essentially a baby picture of the universe when it was just 380,000 years old. While it looks remarkably uniform, satellite missions have revealed incredibly tiny temperature fluctuations within it, ripples that are only different by 1 part in 100,000. These tiny hot and cold spots were the seeds of all future structure. By studying the precise size and pattern of these ripples, cosmologists can determine the exact ingredients of the early universe. This cosmic recipe is astounding. It tells us with incredible precision that the universe is made of 68% dark energy, 27% dark matter, and just 5% ordinary matter. The blueprint for everything that would ever exist was encoded in this ancient light. What cosmic mystery would you want to solve first if you could see the universe in every wavelength of light? Let me know your thoughts in the comments. Now, if you thought dark matter was strange, it's only the second biggest mystery on that cosmic ingredient list. The number one component, making up a staggering 68% of everything, is dark energy. In the late 1990s, 2 separate teams of astronomers were studying distant supernovae to measure how fast the universe's expansion was slowing down due to gravity. But they found the exact opposite. The expansion isn't slowing down at all, it's accelerating. Something is actively pushing the universe apart, acting like a sort of anti-gravity. We call this mysterious force dark energy. Unlike gravity, which pulls things together, dark energy is a repulsive property of space itself. The more space there is, the more dark energy there is, causing the expansion to speed up over time. We have no idea what it is, but we know its effects will dominate the universe's distant future, eventually pushing galaxies so far apart they will vanish from each other's sight. Of course, not everything invisible is as exotic as dark matter or dark energy. Our universe is also flooded with ghostly particles that are part of our standard model of physics, yet they pass through us completely unnoticed. These are neutrinos. They are fundamental particles created in nuclear reactions, like those in the core of our sun. Right now, as you're watching this, hundreds of trillions of solar neutrinos are streaming through your body every single second, yet you feel nothing. That's because they barely interact with other matter. A neutrino could pass through a light year of solid lead with only a 50% chance of hitting a single atom. This makes them incredibly difficult to detect. To even catch a handful, scientists have to build gigantic detectors, often filled with thousands of tons of ultra-pure water, and place them deep underground in mines or even under Antarctic ice to shield them from all other cosmic radiation. Their elusiveness once made physicists think they were massless, but we now know they have a tiny amount of mass, a discovery that opened a new crack in our understanding of fundamental physics. Ultimately, all of these components, both visible and invisible, come together to form a breathtakingly beautiful structure on the largest possible scales. The universe isn't a random scattering of galaxies, it's organized into a colossal network known as the cosmic web. This web consists of vast, interconnected filaments of dark matter stretching for hundreds of millions of light years. Galaxies and galaxy clusters form like shimmering dewdrops along these invisible threads. In between the filaments are enormous, barren regions of near-total emptiness called cosmic voids. The dark matter acts as the underlying scaffolding, its gravity pulling in gas and dust, which then collapses to form the stars and galaxies we can see. So when you look at a map of the universe, you're not just seeing a random pattern of light. You're seeing the glowing, visible tracer of an unimaginably vast, invisible structure that forms the very skeleton of our cosmos. Imagine for a moment that all of human knowledge is a single brightly lit room. We've spent centuries exploring every corner, mapping every detail. But the room has walls, and beyond those walls is an endless, echoing darkness. Now, we're going to press our ears against those walls and listen to the whispers coming from the other side. We've charted the known, but the real adventure begins at the very edge of what we think is possible, where the biggest questions in all of physics are waiting. Our first whisper comes from our own cosmic backyard. We know the Earth orbits the Sun, and the Sun orbits the center of the Milky Way. But our entire galaxy is also on a journey. It's hurtling through space at a staggering 2.2 million kilometers per hour. For decades, we thought this was just the leftover momentum from the Big Bang, but it's not. We're being pulled. Something immense, a gravitational anomaly, spread out over hundreds of millions of light years, is reeling us in like a fish on a line. It's called the Great Attractor, and the strangest part, we can't get a clear look at it. It lies in a direction ominously called the Zone of Avoidance, an area of the night sky completely obscured by the gas, dust, and stars of our own galactic plane. We can detect its influence, we can feel its titanic pull, but its true nature remains one of the greatest mysteries in cosmology. We are being summoned by a ghost. This mysterious pull on our galaxy is a local drama, but it's part of a much larger, universe-spanning story. The very fabric of space-time is expanding, and not only that, the expansion is accelerating. The culprit is thought to be a force we know almost nothing about: dark energy. This enigmatic pressure, which makes up nearly 70% of the universe, is the ultimate cosmic opposite of gravity. While gravity pulls things together, dark energy pushes everything apart. This leads to some wild possibilities for the ultimate fate of the cosmos. One of the most dramatic is the Big Rip. In this scenario, the repulsive force of dark energy eventually becomes so powerful that it overwhelms everything else. First, it would tear apart clusters of galaxies, then the galaxies themselves. As the end nears, it would overcome the gravity holding solar systems together, then the chemical bonds holding planets and even our bodies together. In the final fraction of a second, the expansion would become infinite, ripping apart atoms themselves until the universe is nothing but a sea of fundamental particles, unable to interact ever again. From the end of the universe to the end of information itself, let's talk about black holes. According to Einstein's theory of general relativity, once something crosses a black hole's event horizon, it's gone forever. But a fundamental law of quantum mechanics states that information can never truly be destroyed. It can be rearranged, scrambled, or hidden, but the underlying information that describes a particle must always persist. This creates a spectacular contradiction known as the black hole information paradox. If you throw a book into a black hole, is the information contained in its pages, the arrangement of its atoms, erased from existence? Stephen Hawking proposed that black holes slowly evaporate through a process now called Hawking radiation. But his initial calculations suggested this radiation was random, containing none of the information that fell in. This has sparked a 50-year debate that strikes at the heart of reality. Resolving this paradox will likely require a new theory of physics, one that finally unites gravity and the quantum world. Uniting those two worlds is the ultimate goal, and it forces us to consider reality at its most fundamental, mind-boggling scale. If you could zoom in on an empty patch of space, smaller and smaller, past molecules, past atoms, past quarks, all the way down to the smallest possible length, the Planck length, a distance so small that if an atom were the size of the known universe, the Planck length would be the size of a single tree. You wouldn't find a smooth, placid emptiness. Instead, many physicists believe you'd find a roiling, chaotic cauldron of quantum energy. This is space-time foam. At this infinitesimal scale, the uncertainty principle takes over, and space-time itself is thought to warp and bubble violently. Tiny, fleeting wormholes and virtual particles pop in and out of existence in an endless dance. This theoretical foam is the texture of reality itself, a turbulent quantum ocean upon which our entire, apparently smooth universe is just floating. It's a completely different reality hiding just beneath the surface of our own. If you could somehow peer into this quantum foam, what do you imagine you would actually see there? Share your most creative ideas in the comments. This disconnect between the smooth world we see and the potentially chaotic quantum world beneath hints at another profound puzzle. We've talked about the four fundamental forces: the strong and weak nuclear forces, electromagnetism, and gravity. But have you ever stopped to think about how bizarrely weak gravity is? It's not just a little weaker, it's astonishingly, absurdly feeble. A simple fridge magnet can lift a paperclip, meaning its tiny electromagnetic force is easily defeating the gravitational pull of the entire planet Earth. This is the hierarchy problem. The force that holds galaxies together and dictates the structure of the cosmos is trillions and trillions of times weaker than the other forces. Why? One of the most mind-bending potential answers is that we don't feel gravity's true strength because most of it is leaking into extra hidden dimensions of space that we can't perceive. In this model, our three-dimensional universe might be just a membrane or brain floating in a higher dimensional reality, and we only experience a tiny fraction of gravity's real power. The baffling weakness of gravity is just one of physics' grand numerical mysteries. Perhaps the most embarrassing is the cosmological constant problem, which has been called the worst theoretical prediction in the history of physics. When physicists try to calculate the amount of energy that should exist in empty space, the vacuum energy that drives cosmic expansion, based on quantum field theory, they get a specific number. When astronomers actually measure the expansion of the universe and calculate the value of this energy, they also get a number. The problem is, the two numbers don't match. They don't even come close. The theoretically predicted value is 120 orders of magnitude larger than the value we actually observe. That's a 1 followed by 120 zeros. It's a discrepancy so colossal that it's like measuring the width of the North American continent and being off by a distance larger than the entire observable universe. It tells us, in no uncertain terms, that our understanding of reality is profoundly and fundamentally incomplete. This leads us to our final, most unsettling question. When our theories produce such absurdities, and when reality at its smallest scale might be a chaotic foam, we have to consider more radical ideas. What if the universe isn't fundamental at all?
The simulation hypothesis proposes that our entire reality could be an incredibly advanced computer simulation. This isn't just a philosophical thought experiment, it has roots in physics. Some physicists argue that if a civilization could create such a simulation, they would likely run countless versions, making it statistically more probable that we are in one of the simulated universes than the one base reality. Clues might even exist in the laws of physics themselves. The fact that there's a smallest possible length, the Planck length, could be seen as the pixel size of the universe. The fact that the universe is governed by strict mathematical laws rather than chaos could be interpreted as the underlying code of the simulation. We are peering at the edge of knowledge, but perhaps we are really just peering at the edge of the program. And with that, we're left to wonder if the ultimate question of physics isn't what is the universe made of, but who or what wrote the code? What if I told you that everything you see, everything you feel, your entire three-dimensional existence might be nothing more than a complex hologram projected from the edge of the universe? We've journeyed through the realms of the incredibly small and the unimaginably large. But now, we arrive at the very bedrock of reality itself, the ultimate laws that write the cosmic code. It's a bizarre and deeply counterintuitive idea, but a shocking amount of theoretical physics points towards it. This is the holographic principle, a mind-bending concept suggesting that all the information contained within a volume of space, like the room you're in right now, can actually be described by a theory that lives on the boundary of that space. Think of it like the security chip on your credit card. A flat, two-dimensional surface holds all the three-dimensional information about your finances. The universe, according to this principle, could be doing the exact same thing on a cosmic scale. The 3D world we experience could be an emergent property, an elaborate projection of information encoded on a distant two-dimensional surface. This isn't just a random thought experiment, it's a potential solution to one of the deepest paradoxes in physics, like what truly happens to information that falls into a black hole. It implies that what we perceive as fundamental reality might be a grand illusion, and the true laws are written in a lower dimension. This search for a deeper, simpler reality is what drives the quest for a theory of everything. And for decades, the most famous and controversial candidate has been string theory. The core idea is that if you could zoom in past atoms, past protons and electrons, past quarks, you wouldn't find a point-like particle. You'd find a minuscule, one-dimensional, vibrating loop of energy, a string. Just like a violin string can vibrate at different frequencies to produce different musical notes, these fundamental cosmic strings vibrate in different patterns. One pattern of vibration appears to us as an electron. A different pattern appears as a photon, another a quark. From this perspective, the entire rich particle zoo we observe is just one cosmic symphony played on these tiny, energetic strings. The beauty of this is that it elegantly unites quantum mechanics and general relativity, the two pillars of modern physics that famously don't get along. The catch? For the mathematics to work, string theory requires the universe to have extra, hidden dimensions of space, perhaps as many as 10 in total. These dimensions aren't like the 3 we move through. They are thought to be curled up or compactified into tiny, complex shapes at every single point in our space, far too small for us to ever perceive directly. If you could visit one of these hidden dimensions, what do you think you'd find? Let me know your most creative ideas in the comments. This mind-bending requirement for extra dimensions isn't just a weird quirk, it's the very stage on which the cosmic symphony is played. And things only get stranger from here. Because as physicists explored string theory, they didn't just find one version of it. They found 5. For a while, this looked like a major failure. How could there be 5 competing theories of everything?
But then a breakthrough unified them all under one, even more mysterious and fundamental umbrella: M-theory. M-theory proposes that the 5 distinct string theories are just different ways of looking at the same underlying reality. It's like describing an elephant by only touching its leg, its trunk, or its tail. You get different descriptions, but it's all the same animal. M-theory is that elephant. It suggests that reality has not 10, but 11 space-time dimensions. In this grander framework, the fundamental objects aren't just one-dimensional strings, but can be higher-dimensional objects called branes, short for membranes. Our entire universe, in some M-theory models, could be a 3-dimensional brane floating within a higher-dimensional space. The M in M-theory is famously mysterious. Its creator has jokingly said it could stand for magic, mystery, or membrane, depending on his mood. It remains one of the most promising yet mathematically impenetrable frontiers in the search for the universe's ultimate lawbook. But sometimes, the most profound laws aren't about adding complexity, but about revealing an astonishing simplicity. Take black holes. We imagine them as monstrously complex objects, but according to physics, they are the simplest things in the entire universe. This is captured by the elegant no-hair theorem. It states that once a black hole forms and settles down, it can be perfectly described by just 3 properties, and 3 properties only: its mass, its electric charge, and its angular momentum, or spin. That's it. All the other information about the star that collapsed to form it, whether it was made of hydrogen or iron, whether it was shaped like a sphere or a cosmic potato, is completely lost, shaved away as if by a cosmic barber. This baldness of black holes is a profound statement about how gravity scrubs away information, leading to objects of pure, terrifying simplicity. What other simple but profound laws of nature fascinate you the most? Share your thoughts below. This very idea that information about the star is lost forever has created one of the biggest headaches in modern physics. Why? Because it violates another, even more fundamental law, the conservation of information. This law is a cornerstone of quantum mechanics, and it states unequivocally that information can never be created or destroyed. It can be scrambled, hidden, or rearranged, like burning a book. You can't read the words anymore, but in principle, if you could collect every single particle of ash, smoke, and heat, you could reconstruct the original information. It's never truly gone. So, when something falls into a black hole, the no-hair theorem says its information is erased from the universe. Quantum mechanics says that's impossible. This contradiction, known as the black hole information paradox, is a colossal clash between our 2 best theories of reality, and physicists are still battling to figure out how the universe resolves it. The answer likely lies in the very nature of space-time and information itself. The universe's rulebook has other shocking surprises too. For the longest time, we assumed the laws of physics were perfectly symmetrical. If you took an experiment and ran a perfect mirror image of it, you should get a perfect mirror image result. This concept is called parity, or p-symmetry. And for gravity, electromagnetism, and the strong nuclear force, it holds true. But in 1956, a stunning experiment proved that for the weak nuclear force, the one responsible for certain types of radioactive decay, this symmetry is broken. The universe, at a fundamental level, can tell the difference between left and right. It has a preferred handedness. This discovery of parity violation was so shocking that the physicist Wolfgang Pauli famously said, "I do not believe that the Lord is a weak left-hander." But the evidence was undeniable. The universe is not ambidextrous. It has a subtle, built-in asymmetry that is woven into the fabric of reality itself. Does the idea of a left-handed universe feel strange to you? Or does it somehow make perfect sense? I'm curious to hear what you think. And perhaps the greatest twist in our understanding of the universe's laws comes from what Albert Einstein considered his biggest blunder. When developing his theory of general relativity, the equations showed the universe should either be expanding or contracting. To force it to be static, which was the prevailing belief at the time, he added a fudge factor, a term he called the cosmological constant. When observations later proved the universe was, in fact, expanding, he threw the idea out. But decades later, in the late 1990s, astronomers made a jaw-dropping discovery. Not only is the universe expanding, but its expansion is accelerating. Something is pushing space apart, and the best explanation we have is a mysterious anti-gravitational force inherent in the fabric of space-time itself, a dark energy. And the simplest mathematical way to describe this dark energy is with Einstein's old, discarded cosmological constant. His biggest blunder might just be the deepest law of the cosmos, the intrinsic energy of empty space that is driving the ultimate fate of our universe. Einstein called it his biggest blunder, but it might be the key to everything. What do you think is the biggest blunder in history that turned out to be a genius discovery? Drop your answer below. This constant, once a simple mistake, now represents the single biggest component of the universe's energy budget, a final, mysterious rule in the cosmic code we are only just beginning to decipher. We've journeyed from the subatomic dance floor to the edge of the observable cosmos, through the birth and death of stars, and past the twisted fabric of space-time itself. But the final part of our story isn't about the solid ground of proven theories. It's about the blank spaces on the map, the regions marked "Here be dragons," where the greatest mysteries still reside. This is the unwritten story of our cosmic future. Everything we see, our galaxy, the Andromeda Galaxy, and 100,000 other galaxies in our local supercluster are all being inexorably pulled toward a single unseen point in space. This isn't just standard gravitational drift, it's a directed, high-speed flow toward a gravitational anomaly known as the Great Attractor. Located about 220 million light-years away, its exact nature is shrouded in mystery, hidden behind the plane of our own Milky Way in an area called the Zone of Avoidance. For decades, we couldn't figure out what was exerting such a colossal pull. We now know it's the gravitational focal point of the Laniakea supercluster, a truly incomprehensible collection of galaxies that includes our own. So, while the universe expands, our entire cosmic neighborhood is hurtling at 2.2 million kilometers per hour toward a gravitational mystery we can barely even see. While this cosmic undertow pulls us locally, an even greater force is working on a universal scale, pushing everything else apart. This is dark energy, and it's not just a small background effect. It is the dominant component of the cosmos. Current measurements suggest that a staggering 68% of the total energy density of the universe is this mysterious, repulsive force. Unlike gravity, which pulls things together, dark energy seems to be an intrinsic property of space itself, causing the expansion of the universe to accelerate over time. We have given a name to the single biggest thing in the universe, and yet we have absolutely no definitive idea what it is. Is it a cosmological constant, as Einstein once proposed, or some new dynamic field that changes over time? The answer will determine the ultimate fate of everything. And the ultimate dominance of this dark energy is what will likely write the final, silent sentence of the universe's story. The leading theory for the end of the cosmos is not a fiery crunch, but a slow, creeping cold known as the heat death or the Big Freeze. As dark energy continues to push galaxies apart faster and faster, they will eventually accelerate beyond each other's cosmic horizons. An observer in the far future would look out into the night sky and see nothing but the few gravitationally bound galaxies in their own local group. The rest would have effectively vanished from the observable universe forever. Eventually, star formation will cease, the last stars will burn out, and even black holes will evaporate over unimaginable timescales through Hawking radiation. The universe will become a vast, cold, dark, and empty place, approaching a state of maximum entropy from which no useful work can ever be extracted. A quiet, eternal end. But even in a cold, dead universe, one cosmic law must be upheld. Information cannot be destroyed. This created a huge problem for black holes, which seemed to swallow information forever. The resolution to this information paradox is the holographic principle, a staggering concept suggesting that all the information contained in a three-dimensional volume of space, like the inside of a black hole, can be fully described by a two-dimensional surface at its boundary, like the event horizon. It's as if the universe is a hologram. This isn't just a metaphor, it's a mathematically rigorous idea emerging from string theory and quantum gravity. It implies that the 3D world we experience might be a projection of information stored on a distant 2D cosmic surface. Our solid reality could be an intricate illusion. If the nature of dark energy is different from what we suspect, the end could be far more violent. Another possibility for the end of the universe is the Big Rip. In this scenario, dark energy is not a constant, but a form of phantom energy that grows stronger over time. As its repulsive force increases, it would begin to overcome the fundamental forces of nature one by one. First, it would tear apart superclusters of galaxies. Then, it would overcome the gravity holding individual galaxies together. In the final moments, its power would be so immense it would unbind star systems, and then overwhelm the electromagnetic force holding planets and even atoms together. In the last fraction of a second, space-time itself would be torn asunder. It's a dramatic and terrifying alternative to the slow freeze, entirely dependent on the true nature of that dark energy we're trying so hard to understand. Whether the universe ends in a rip or a whisper, it begs the question, is this the only universe? The theory of cosmic inflation, which so elegantly explains the flatness and uniformity of our own cosmos, also predicts that inflation doesn't stop everywhere at once. It could be that our universe is just one bubble that stopped inflating, while all around us, the process of inflation continues eternally, spawning an infinite number of other bubble universes. This is the multiverse. Each of these universes could have wildly different physical constants and even different laws of physics. Some might be dead and empty, others might be stranger than we can possibly imagine. We may never be able to prove they exist, but they are a natural, almost unavoidable consequence of our best theories about how our own universe began. And as we contemplate infinite universes, we're forced to confront the single most profound tool we have for understanding even one of them: mathematics. Physicist Eugene Wigner spoke of the unreasonable effectiveness of mathematics in describing the natural world. Why is it that abstract, formal systems of numbers and symbols, often developed with no real-world application in mind, turn out to be the perfect language for reality? From general relativity to quantum mechanics, equations on a blackboard have predicted real, observable phenomena with breathtaking accuracy. Is mathematics an invention we use to model the universe? Or is it a fundamental discovery, an intrinsic language that the universe itself is written in? This mystery sits at the very foundation of science, suggesting a deep, almost mystical connection between the human mind and the cosmic order. It might be the most fundamental fact of all, that the universe is, for reasons we may never fully grasp, understandable. From the first spark of curiosity to the grandest theories of cosmology, we've seen how physics weaves together the story of everything. It's a story of impossible scales, of elegant laws, and of mysteries that still call to us from across the cosmic ocean.
The final chapter isn't an ending, but an invitation. The story is still being written, and the next page is blank, waiting for the next discovery, the next question, the next leap into the unknown. If this journey through the cosmos has expanded your mind, be sure to hit the like button and subscribe for more explorations into the biggest questions in the universe. Thank you for watching.